My name is Enes Göktaş, and I'm going to present our work, which is on mitigating advanced code reuse attacks at the binary level. So I share the first authorship with Victor van der Veen, who's sitting there. So control flow integrity is a very promising technique to stop code reuse attacks. What it actually is doing is it enforces certain constraints. So control flow integrity actually modifies the program such that it enforces certain constraints during runtime, which actually hinders the capabilities of attackers. However, it is not that easy to enforce a very good control flow integrity in a program, especially at the binary level, where you don't have the information that's available in the source code. So existing binary level CFI solutions, these are not able to to prevent function reuse attacks, so the more advanced code reuse attacks. This is called, so one of these attack techniques is called COOP. So we developed Type Armor, which is a binary level CFI solution, but a more precise one than the current state-of-the-art binary level solutions. It stops all published code reuse attacks with an acceptable and comparable overhead of about 3% on spec. So what we try to do is we try to get as close as possible to source level solutions. So in source level solutions, they they look at the types of functions, and they use certain information, and we try to get actually close to this solution. So let me try to give you an idea of what advanced code reuse attacks are. So what are attackers doing in such advanced attacks? So here we have a piece of code, a function that contains a while loop, which contains an indirect call. And this indirect call uses the f pointer variable to call different functions. So at runtime, this f pointer variable is being loaded with the address of a function, and then at runtime it calls this function, the loaded function. And this can also be another function at the same indirect call. So it's not a direct call. It can be different functions at different moments in program. But here we take 3 functions from the program. Among others, we take function 1 as an example. So this indirect call is allowed to call function 1, but not function 2 and function 3. Okay, it's not working. Okay, so what does an attacker do? The attacker gets control over this indirect call with some vulnerability. So it gets control of this f pointer. It loads its own, the address of its interested function, for example, function 2 and function 3. So what an attacker does in this advanced code reuse attacks is it uses this indirect call within this loop to call multiple functions after each other. So it also gets control of this while loop, actually. And then it calls multiple functions after each other to perform its desired functionality. The functions that perform the functionality are we call gadgets, and the main loop gadget we call loop gadgets. And this is function-oriented programming. So, however, binary level CFI solutions, they are unable to resolve the exact targets of this indirect call. So they do raise the bar for attackers. The indirect call cannot go anywhere in the program, but to a limited set of targets, but to all functions in the end. And this allows attackers to still perform the advanced code reuse attacks. So it would allow this indirect call to go to all these functions. So at source level, you have all the information. You can extract the targets for all indirect calls, and you can enforce this information during runtime. For example, VTV enforces the class hierarchy information to actually enforce this constraint at runtime, and this allows, for example, this indirect call to go to unintended locations like function 2 and function 3. IFCC the same. However, this technique enforces the, leverages the function argument types available at source code. So what is type armor doing? So type armor tries to approximate the source level accuracy, tries to get close to the source level available information. However, it is not as accurate as source, so it allows certain unintended functions still. However, it does stop more than the current binary level solutions. So it, for example, it stops for the third function, function 3. So we are somewhere in between the current state-of-the-art solutions and the source level solutions. Okay. How do we approximate the source level accuracy? So what do we extract from the binaries? We perform function signature matching by extracting argument counts at the indirect call sites and the functions. So at the indirect call sites, we do some analysis and we look for arguments being prepared, and we use that as the invariant at the indirect call site. And we do a similar thing at the functions, where we look at arguments being used. And then once we have this information, we mark the indirect call sites and the functions with the argument count, and then we perform some matching. So only functions that match with indirect call sites, only these are allowed to be performed during runtime. So let's give an example. Assume that we have an indirect call site and type armor determines that it prepares 2 arguments. Then this indirect call site is not allowed to call functions that actually expect 3 or more arguments. We have implemented type armor for 64-bit architecture, where the calling convention is that the first few arguments, when a function is called, is given through registers. So when we do the analysis at the indirect call site and the functions, we look for instructions that, at the indirect call site, we look for instructions that actually write to these register arguments. And at the functions, we look at instructions that read the register argument before it is written. So it uses the value that has come in the function. Okay, so let's give an example. So we match, once we have the information, we match the call sites and the functions, and depending on the types, we either allow or disallow the link. For example, at this indirect call site, type armor determines that it prepares 2 arguments, and at function 1, it also determines that it expects 2 arguments. Type armor would allow this link to be performed. The same applies for function 2, where type armor determines that it actually also expects 2 arguments, and it would allow again the link, the control flow from the indirect call to this function, function 2. However, at function 3, it determines that it expects 3 arguments, and as a result, type armor disallows this indirect call to go to function 3 because the matching didn't succeed. So how accurate can we determine the prepared and the used argument count at the indirect call sites and the functions? We have evaluated some widely used applications, servers, including memcached, lighttpd, Nginx, and MySQL. Memcached is a distributed server, memory cached, that performs memory caching. Lighttpd, Nginx are HTTP servers that serve websites, and MySQL is a database. The first 3 servers are C programs. MySQL is a C++ program. And you can see that MySQL is actually well, a lot more complex. It contains lots of indirect calls and lots of address taken functions. We can notice actually that we get quite close to the source code in determining the argument counts. For example, for MySQL, we can determine, well, type-armor determines that, finds that about close to 6,000 call sites. So it's able to determine precisely the argument count for 6,000 call sites out of 7,500. And for functions, it is able to determine precisely for about 7,000 out of 10,000 functions, the argument count it expects. So once we have this information, how do we enforce it during runtime, like the matching? We insert checks before the indirect calls, and we insert the IDs, which are the expected argument counts at the functions. We insert it before the function entry point. Once the indirect call is about to be called, it performs the check. It retrieves the ID of the function that's targeted, and then it performs a check. This check does, is the ID of the targeted function within my reach? And that is, it checks whether the target ID is less or equal to its own ID. So in this case, this indirect call could go to functions that have 0, 1, or 2 arguments. Okay, so we also performed some performance evaluation to compare our solution with the others. And we performed the performance evaluation on spec, where we had, well, acceptable performance overhead, less than 3% in geometric mean. We again evaluated some servers, and here we could see that actually security comes with a price. So improved security can give actually also quite some performance overhead. We saw in MySQL, which is our worst case performance overhead, which is in C++, had a performance overhead of 24%, but the others had far less performance overhead. And we think that MySQL executes an immense amount of indirect calls in its critical path. As to conclude, we extract new invariants from binaries that were not evaluated before, extracted before, and we use this information to apply the strictest security policy at the binary level known to date. And we actually also show that binary level CFI solutions can mitigate advanced code reuse attacks. Also, we are planning to make type-armor open source, so keep an eye out on our webpage, vusec.net. Thanks for listening, and I'm happy to accept questions.
Hi, thanks for the talk. So you showed like 70–80% precision rate for finding argument counts at both call sites and at functions. When you're wrong, are you consistently over or under? Or do you have cases where you have accidentally over counted the number of arguments for a function or undercounted the number of arguments of a call site, and thus will block legitimate calls when there's no attack present and cause the program to crash?
Yeah. So we tried to be as conservative as possible. So during the analysis, well, we tried to, at the indirect call site, we tried to overestimate, and at the function underestimate. So that was the idea. And then we couldn't find any case where the program would break. So, yeah.
Okay, and what do you do with like varargs functions?
Like, sorry?
Like printf, right?
Oh,
what
yeah.
do you do with printf?
Yeah.
Because printf is like attack complete.
Yeah, so we look for, we do some pattern matching for such functions. So if printf, let's say, is address taken, yeah, okay, printf itself. I'm not sure if it's address taken, but the program itself can have a printf-like function which can be address taken. And for such functions, for functions with variadic arguments, we do some pattern matching. So you have this specific piece of assembly in such functions. And then there you can extract, you can see how many are actually exactly set, and then the rest is variadic. And then we take this exact argument count that we can detect there.
Okay.
I think he asked my question already.
All right, so Vasilis Kemerlis, Brown University. So when you identify arguments, you rely on the fact that you know the calling convention, which is x86-64, and which arguments pass in registers, and so on and so forth. How do you handle static functions? When a compiler compiles a static function, yeah, and a function that is not exposed in a compilation unit, there is no requirement to respect the calling convention. So how do you identify the arguments there in such cases?
So in static functions, so which are not address taken, you mean? Or I think
You can have static functions which are address taken and are assigned to function pointers.
Okay, what's the problem you're seeing there?
So the problem is that how do you know, you rely on the calling convention to identify the arguments, right? And the compiler, when it compiles that, doesn't need to follow the calling convention. It can do whatever it wants because the function is not exposed outside of the compilation unit.
So I think if it is address taken, I don't think the compiler can do whatever it wants, I think. Okay, we will have a look at it, but I think if it's address taken, it has to follow rules that apply to address taken. So I think that priority is higher than if it's address taken.
All right, thanks.
Hi. So I have another question. Does your tool handle calls based on the register-based calls when the address is in the register, not in the memory? Compiler can do those kind of things, right?
I'm sorry, I think I couldn't understand.
So the example that you showed,
Yes.
it was a call F pointer. So
Yeah.
F pointer is holding the address of the call.
Yeah, exactly.
But there are certain situations in which compiler uses register-based calls. It uses the
Yeah.
registers to make a call.
Yeah,
So
yeah.
do you address those
Yes,
things
yes.
in
So
it?
during the binary instrumentation, we take so we look at the call, the indirect call, and then we extract the target based on how the call is making the call actually. So if it is register, we get the address from, the value of the register. If it's a dereference on the register, we also dereference that register to get the target.
Okay, so at the part of the tool analysis, you make sure that if it is not an indirect call based on the memory, then you actually try and look for if it is making a register-based call.
Yeah.
I have a couple
But we
of other
can
questions, but
specify.
I'll take offline.
Yeah, sure.
Hi, I'm Nathan Burrow from Purdue. I was curious, your tool relies on function signatures. Do you have any insight into how many functions in a program have the same signature according to your tool? And if that group is large enough to still make code reuse attacks within that group of functions with the same signature practical?
Okay, it's a very good question. No, I don't have the answer right now.
Okay, thank you.
So I noticed you mentioned in your abstract a little bit about the coup attack. Can you talk a little bit about why your solution, since it's still not fully precise, mitigates that attack? I guess I just don't understand that link there.
Why it does not mitigate?
Why it does mitigate? You had a blurb in your abstract, and maybe I should just read the paper. But why? Like what's the interaction between this additional precision and the coup attack?
So during the coup attack, it uses the main loop, the loop gadget, where it has one indirect call site, and it calls different functions, right?
Okay.
Okay, so we look at the indirect call site, and in the examples so in advanced code reuse attacks we looked at, we could see that the indirect call that was used in the main loop did not match with at least one of the functions that were called. So in that way, we could stop the attack.
To be clear, you were just looking. Did you look to see if like there were other functions that were still allowed under your scheme that could have replaced the ones that were used in the coup attack?
No, we didn't look at to harden the available exploit. We didn't have a look at it.
Okay.